Oh, not that one, not that one. Okay. All right. So this is going to feel a little bit weird. And what I would say, just because it's like a lot of big ideas and kind of background information that we need before we can move on into this chapter. So I wouldn't even suggest really trying to start a whole lot of the homework. There's probably only a couple questions you could do before Wednesday. So maybe instead of spending study time on homework today or tomorrow, I would recommend rereading this first section or two. What is this, 2 and 3? Just to kind of re-solidify the concepts. So I will say that I'm going to introduce some big ideas, and you need to be able to get to the end conclusions. Like, you need to understand the end conclusions, but you don't necessarily have to understand all of the little steps of how we got there. So it's going to be helpful so that you don't just, like, if I say, okay, this is one of our big conclusions, is that energy can be transferred through heat and work. That's maybe not going to mean a whole lot to you if you don't at least have a vague idea of how we got to that point. But it's not like I'm going to have you working through all the steps. Does that make sense? I'll try to kind of reiterate that as we go through. Like, what are the big key takeaways that you're going to have to take and continue on throughout the unit? Okay, like we'll talk about law of conservation of energy on the next slide, and I'll do all this weird, like, if this is true, then this is true, then this is true. It's not like you're going to have to repeat that back, but when we get to an end point, you're going to have to take that and move forward with it. Okay, so I want to give you more of an overview to start, because I always think it's good to have a context of where we're heading. And a lot of today will be kind of going back and forth through the same few ideas in a few different ways, okay? So this is chemistry class, so we care mostly about chemical reactions. So with a chemical reaction, we have some reactants, and they are going to form products. So we will use the word system a bunch today. And in the end, by the end of this chapter, we're going to really care about as far as a system is the chemical reaction, or the reactants and the products. When we talk about energy exchange in chemistry, that's what thermochemistry or thermodynamics means, is it's specifically thermo implies heat. We talk about other stuff too, but it's mostly energy transfer through the transfer of heat. When we talk about that, we need to talk about where that heat is going. So we're going to talk about the surroundings. And in reality, the surroundings is literally everything else other than the reactants and products. Like everything else in the universe. Okay, that's not very practical to like measure everything else in the universe. It's not possible. So a lot of the times we will we'll make assumptions. Like if you remember, if you took high school physics, do you remember like all the time they would be like, let's imagine a frictionless surface. Like there's no frictionless surfaces, right? At least nothing that we're actually familiar with. So we make assumptions so that we can kind of do the basic things, and usually they're good enough. We'll do some stuff like that. If you remember, I think last semester in the lab, you guys did something with a coffee cup and measured temperature changes. Does this sound familiar at all? No? You can look at Maggie. I feel like Maggie would remember. So we'll use insulation. So if we had like a cup that had fairly decent insulation, had some water in it, and then we had a chemical reaction. We'll abbreviate reaction RXN. I realize there's not an X in the word reaction. That's how we abbreviate it. If we had a reaction going on in water, so this could be like something as simple as dissolving salt, okay? So we have some chemical reaction occurring in the water. We can actually consider that the surroundings is just the cup and the water, because the cup is kind of a good enough insulator that if any heat is lost or absorbed, it'll pretty much just stay within that cup. Sure, some of it's going to get lost to the air around it, but it's minor enough that we just make the assumption that the water in the cup alone are the surroundings. Okay, so system is reactants and products. Surroundings is technically everything else, but we're going to simplify that down and make some assumptions so that it's easy to deal with. Okay, so when we talk about this, we're going to be talking about energy exchange between those two. Okay, so this is where we're heading, is by the end of class today, we're going to have a couple different ways to, in a diagram illustration form, represent how energy gets exchanged between the chemical reaction and the surroundings. We're going to talk about not actual values yet, like how many units necessarily get exchanged, but we're going to focus in a lot on the sign. So like, is something have a positive change in energy or a negative change in energy? And then we're going to talk about the two most common ways that energy gets exchanged, which are heat and work. So I'll introduce those briefly at the beginning. We'll do kind of a formal introduction of the big concepts, and then we'll go in a little bit more detail. And like I said, we'll show you these diagrams and stuff. So when you come in on Wednesday, we can actually do calculations, and you'll know what those calculations mean in terms of, is the reaction losing energy? Is it losing it as heat? Is the reaction absorbing energy? Every time we talk about energy changes in a reaction, I want you to remember, I'm sick of dropping my pencil. I don't want to break it. My keys? Okay, so every time we talk about a chemical reaction, I want you to get the analogy of gravity, right? So if my keys are the reaction and I hold them up here and then I let them go, we know that they're going to fall, right? They're at a high potential energy and they go to a lower potential energy. So that difference in energy has to go somewhere. It doesn't just get lost. That's going to be on the next page. The law of conservation of energy. It doesn't just disappear, it goes somewhere, okay? So in case you missed it the first time, what happens, it gets converted into energy of motion, right? This is very basic physics. You've got a high potential energy, it goes to a low potential energy. That amount of energy gets converted into kinetic energy. Eventually, it gets converted into a force that's, put into my bag. But that energy gets transferred between things. So we're going to come back to the example of gravity quite a bit. And we're going to keep using this idea of energy. Now, technically, your book will use this term internal energy. It really just means all of the kinetic and potential energy of a particular thing. Okay, so in the example of my keys, the keys at the beginning had no kinetic energy. They had all potential energy. As they moved further and further down, that potential energy was getting converted to kinetic energy until they had a minimum amount of potential energy. And they had a lot of kinetic energy right before they hit my bag. And then all that kinetic energy got dissipated into the chair and my bag and whatever. So in particular, we are going to spend a lot of time talking about the potential energy associated with the reactants and products. And all of that, if you remember from when we talked about bonding, comes from the negative, positive attractions between electrons and nuclei. A lot of the times when we're talking about bonding, it's between electrons of one atom and the nuclei of another nucleus. So let's start with like a really simple chemical reaction. I gave this example at the beginning of my last class, and then I realized that I use it later on in one of the pictures, so it works out well. So let's look at carbon and oxygen gas. So I'm actually going to draw a basic Lewis structure for the oxygen gas, so you remember that there's a double bond there. And then when those combine in the right circumstances, they will form CO2. Okay, so that now has a double bond between oxygen and carbon and the other oxygen and carbon, but it no longer has that oxygen-oxygen double bond. The difference between the potential energy of these chemicals and what has to happen for them to turn into this one and then create a new potential energy in that CO2, that is what we're talking about when we talk about a change in potential energy. Okay, so before I even scroll down to where it's heat and work, I want to talk about how we define change, and in this particular example, where that change in energy is coming from. So change is always going to be defined as final, whatever your final state is minus your initial state. Yes, I do have that right there. Okay, I'll scroll down ever so slightly. So in terms of a chemical reaction, the final state is always that of the products, and the initial is that of the reactants. So in our example above, carbon plus oxygen forms CO2. What we really want to know in order to calculate an overall change in energy of that reaction is we would want to know the energy of CO2, and really we would be talking about the potential energy. I realize we say energy is kinetic plus potential, but the thing that's going to be changing in a chemical reaction is the potential. The kinetic's going to stay relatively similar. And then we would subtract off the energy of the carbon and the energy of the oxygen. So I'll just tell you right now, the CO2 bonds, the C double bonded to O, those are lower in potential energy than if we have the oxygen and the carbon separate. So this is similar to the gravity example, okay? We've got the carbon and oxygen up here. That looks confusing because I've written them so close to each other. Carbon and oxygen. And then down here, we would have the CO2. So this would be like my keys dropping. We go from a high potential energy to a low potential energy. Now, by the end of the chapter, we can actually calculate. It's not perfect, but it's pretty good. We can calculate this change in energy by looking at how much energy does it take to break this bond, and then how much energy is released when those two bonds form. So please, please, please don't forget, breaking bonds takes energy, right? Because they're attracted to each other. You got to break them apart. And forming bonds releases energy. So at its deep core essence, the change in energy of a chemical reaction is the difference between how much energy does it take to break this guy up and how much energy is released when these guys form their bonds. That really is what we mean when we talk about a change in energy of a chemical reaction. Energy required to release those bonds, energy released when those bonds form. In fact, I think we're going to skip, no, I think I know. I know we're going to skip the kinetics chapter, which is where we talk about activation energy. It's like the one topic that I'm really sad we don't do, but the rest of kinetics is just a beast. So if you have done biology, you probably are familiar with the idea of activation energy. So when we look at an energy diagram, there's a certain amount of energy you have to put into a chemical reaction to get it started. So the example would be like striking a match, right? The match releases a bunch of energy once you get it burning. That's, it's releasing energy because you can see, fire coming off of it. That's energy. But you have to strike the match. It doesn't just combust on its own. That would not be good. Similarly, gasoline. We will talk about internal combustion engines today for a second as a good example. Gasoline, you need a spark. You have to have a spark plug in order to get that gasoline to ignite and then produce energy that your car can use to move. So that initial amount of energy, we call it the activation energy, and that really goes into breaking that oxygen-oxygen bonds. We put in a little bit of energy, and then we get a ton of energy that comes out. So this is roughly, this is the energy required to break that bond, and then this big chunk of energy is what comes out when you form those two carbon-oxygen bonds. So you start at a high one, you go to a low one. The overall difference is final minus initial. So that is the big, giant theme for the entire chapter. In 4 class periods, that's where we will end, is by calculating changes in energy using how much energy does it take to break a bond, how much energy does it use to form a bond. But before we get to that point, we're going to talk about a lot of other things related to it. Okay. There's 2 main ways that we see this change in energy occurring with chemical reactions. So heat, we just talked about a match. Heat is one of those. If heat comes off of a chemical reaction, that's one way that a chemical reaction can release energy. The other is work. So you probably don't remember this from physics, but work is a force times a distance. So if I apply a force to the chair and I move it a particular distance, I can't even get it to move very much, there's too much friction. So I move it a particular distance, that's the work that I performed on that chair. So I'm going to, I don't have this, that's just not loading, right? I have to close that in a second and figure out why that's not loading. Okay, I was looking for a blank page and that didn't really help me. Let me just close it and open it again. Okay, I am going to use the example of the gasoline. So we're not going to work through what all the bonds are, but I am going to tell you that, yes, we'll use this. Okay, don't look at this side yet. Let's just look at the system. We're going to pretend that this is our chemical reaction, and we are going to start with octane, which is the primary component of gasoline, and oxygen. So these are our reactants. And we are going to make CO2 and water. So if you remember from Chem 1, this is just like a standard combustion reaction. carbon-hydrogen compound combines with oxygen, produces CO2 and water. These are always releasing energy. They're chemical reactions that release energy, which is a side note. That is a preferred chemical reaction. That is the one that happens more frequently. So if I have my keys and I let them go right here, they're gonna drop, right? Every time they will drop. That's how gravity works. Now, how often am I gonna come along and pick up my keys and put energy into them and move them up higher? It can happen, it does happen sometimes, but much more frequently, they lose energy and go to a lower potential energy state. So that is the more common, more frequent type of chemical reaction, is one where it goes from a high energy to a lower energy. So in this little diagram, this is like, not official. This is just kind of a way that we use to explain what's going on. We have this energy gauge for what we start at. So we'll even give these numbers. This is 1 unit, 2 units, 3 units, 4 units. So initially, we start with 2 units of energy. And then at the end, we end up with 1 unit of energy. Okay, so like I said, change in energy, change is always final minus initial, or the energy of the products minus the energy of the reactants. Okay, so 1 minus 2 in this instance, or the change in energy is equal to -1. Okay, so what that means is that 1 unit of energy was lost. The negative just tells us that energy was released. I would say that the sign, the positive and negative, is like even more important than the actual amount, if I had to pick one, because the sign tells you, did I drop the keys or did I pick up the keys? Did I burn the gasoline or did I take carbon dioxide and water and mush it back together and turn it into gasoline? That's not going to happen, okay? So the negative sign, and this is summarized in a different slide. I'm not going to go there right now. The negative sign tells you that energy is released. If it's positive, it tells you that energy was added into that reaction. Okay, so in this process, energy is released. By our diagram here, 1 unit of energy. So where did that energy go, right? Because the slide above is going to tell us that overall, we can't lose energy. We can only transfer it between things. And what I'm going to get at is that the ways that we transfer it, the 2 primary ways that we're going to worry about, are 1 with heat. We represent that with a Q. We use H for something else. It's a very specific kind of heat that we use H for. Even though it's not called heat then, it's called enthalpy. So that's stupid. Why don't we call that something else? I don't know. Heat is labeled as Q, all right? The other thing that energy can be transferred as is work, which is this force. And as you see in this note, you can always come back to this. Work in chemistry has to do with expanding gases. So let's go back to the idea of and I really should have a picture of like an internal combustion engine here. But let's go back to the example of burning the gasoline. So we have a little bit of gasoline inside the cylinder in your car. There's a spark plug that ignites it, gives it that little bit of energy it needs. And then basically in a controlled way, that gasoline explodes. Okay? So it turns into CO2 and water, and it pushes up, so it expands because it's going from a liquid with a little bit of gas to a lot of gas. So it expands inside of that cylinder and it pushes up on the piston. If you know anything about, if you don't, just Google a picture really quick. So there's a bunch of little cylinders, there's these little caps on top of the cylinders, and each of those little caps moves up and down, and then as they move up and down, that rotates the axle in your car. So a gas expands, pushes up on that piston, that is doing work because it is applying a force. The chemical reaction is actually applying a force in order to move your car along. Also, your engine produces heat, right? If you touch the top of your car, like the hood of your car, after it's been running, it's hot. That's not the thing that helps you move down the road, but it is a byproduct of the chemical reaction. So in this example, the energy is released, and it's released as heat and work. Now, if we were to calculate the exact amounts of heat and work that were released, we would find that those are both negative values as well. So Q would be negative and work would be negative, meaning that they left the system. The system was the thing that released the heat. The system was the thing that did the work. So that's what those signs mean. Okay, now we need to consider the other side of this. Where did that heat go? Where did that work go? And this is when we're going to start talking about the surroundings. So I'm going to use this energy gauge to talk about it, and then we'll go back to the previous slide and explain why this works in reference to the law of conservation of energy. Okay? So you start off with a certain amount of energy here. Now this could have been 1 or 0 or 4 for that matter. The point is it increases by 1 unit. So that 1 unit of energy went to the surroundings. In the case of your car, that's the heat going into your car and into the air surrounding your car, and the work going into moving that piston that then moves the axle, that then moves your car. Okay, so the energy doesn't just disappear, it goes into something else. And we define that as the chemical reaction is the system, it's the thing that's either losing or gaining, and then the surroundings is the thing that either takes it, in this case, or in the opposite case, it would be the thing that gives it to the reaction. They will always be the same amount, so this is still 1 unit. But if we look at it from the surroundings perspective, the sign should be different. So the change in energy of the surroundings would just be +1 because it's the thing that's getting that energy. So positive means it absorbs. So the positive means absorbs. Negative means releases. So in this particular example, the chemical reaction releases energy and the surroundings absorbs that energy. And that is the most common way that we represent that. Or sorry, that we see in chemical reactions. Okay, why does this work according to the conservation of energy? If we divide the overall energy into system and surroundings, like we talked about before, and we say that we can't lose energy in the universe, we just have to move it back and forth. So that's what we mean when we say the change in the universe is 0. Like the sun is losing energy, right? Every time it burns up helium and hydrogen and everything, it loses energy, but then other stuff gains it. Our atmosphere gains it as heat. I think I said this a few times before, certainly in last semester. Heat for chemicals is just molecular motion. So if a chemical, if the air absorbs heat, those molecules are moving faster. So like the molecules in the air outside, they're like this, they're bouncing around, they're vibrating, okay? Their bonds are literally going like this. The ones in here are going a lot faster, okay? They're bouncing around a lot faster. Think about when we did gases. We talked about this a lot. Okay, so the energy just gets transferred. Lots of the times it's heat, but the overall energy doesn't change. So if we divide things up into system and surroundings, but we say overall that change has to be equal to 0, then what we're really saying is that the system and the surroundings are the same quantity. They're just opposite signs, which is what we did just a second ago. We said that if the system, the reaction in the case that we care about, if that one loses 1 unit of energy, then the surroundings would have to gain that 1 unit, which is why the negative is there. We're saying they're opposite signs. So in the example we did before, we said the system was -1 and the surroundings was +1. So that negative there is what makes them equal. So they should always be the same number, just opposite signs. That's because they're transferring it back and forth. And we already talked about this. To calculate that change in the reaction, we could look at the energy of the products and subtract the energy of the reactants. And we'll do that in more detail at the end of the chapter. Okay, I think I have like a little thought example here. Yeah, let's do this first because I think we need a break from me talking. Okay. This first one is going to represent initial conditions for a chemical reaction and the surroundings near it. And I want you to pick the correct one that corresponds to a change in energy of the system, or the reaction is what we mean, that's negative. So choose which one of those corresponds to the correct final state, final conditions. Okay, so our system starts at, we're going to say this arbitrary, gauge, we're going to call it 3, and the surroundings starts at 1. So remember, if the system is negative, that means that it gave up energy. Energy left it. So we've got to pick one where it's less than 3, okay? So it can't be C, because that shows it increasing. This would be where the system is positive, okay? Both of A and B go down to 2. So either one of those looks right for the system. But remember, they're both going down to 2, we said. Remember, that energy has to go to something else. It doesn't just disappear. So if the system goes down by 1 unit, the surroundings then needs to go up by 1 unit. So it's got to be this one. So the system went down from 3 to 2. The surroundings went up from 1 to 2. Are we okay with this? Okay. This is a good way to understand what's happening. The preferred way, and what we'll talk about, what we'll do most of the time, is with an energy diagram that is similar to this. So for a second, don't look at this side for a second. I need to show the whole thing because I need you to be able to see all of that side, but just don't look at the left or the right-hand side for now, okay? When I draw these, I'm going to draw the reactants kind of to the left and the products to the right so that it looks like you're reading a chemical reaction from left to right. So just be aware of that I'll kind of stagger these. And maybe I'll write down what the reactants and products are, or maybe I'll just write R and P. So the most common way that we represent this is with these style of energy diagrams, where if it's higher in energy, you write it higher up on the diagram. Technically, we should always draw an arrow and say this is energy, so high energy is up here, low energy is there. You can assume if we're drawing it higher up in the paper, that it's higher in potential energy. Okay, so this is that same example we did earlier, carbon and oxygen coming together to form CO2. So the reactants start higher, carbon and oxygen are higher in potential energy, the products are lower in potential energy. So this is kind of summarizing all of these ideas. That means the energy, if it is going down in energy, that means that energy has to go somewhere. So a lot of the times you'll see me draw this arrow of something coming off. Heat or work, okay? So that energy is coming off, which means that your change in energy should be negative, the change in energy for that reaction. Okay, so energy is flowing out of the system is negative, but remember, if it's losing energy, the surroundings has to be opposite, so the surroundings is positive. Here's another way of representing that. You've got a negative change in energy for the system, positive for the surroundings, so that means the energy is going from the system to the surroundings. So same thing as the gasoline example. Heat's coming off of that chemical reaction. You're going to physically feel it as hot, or it's making gases that are pushing out on something. And then if we were to look at the opposite direction, so this is now we've just flipped the chemical reaction around on the other side. So again, this is just like trying to summarize these two different cases in a few different ways, but all in one place, so you kind of see how they're all connected. Are they lined up with the... Yeah, they're sort of lined up with this too. So this one would be the one where you have negative change in energy of the system. This one would be positive change in energy of the system. Oh, that's the surroundings though, so never mind. Don't pay attention to that. It only works for the one on this side, not this one. Okay, let's just flip the chemical reaction around. Now, it'd be kind of nicer if we had a totally different chemical reaction, but we can do it with the same one if we just turn it around. So now we start with CO2. Okay, we start with CO2 and we break it up into its original elements, carbon and oxygen. So now the reactants are down here at the bottom because the CO2 is a reactant now because we've turned it around. The products are up here at the top, which means that we picked the keys up, okay? So I had to put energy in. I'm the surroundings. So energy flowed from the surroundings into the system to get this to occur. That's because it was going up in energy, right? I can't make something go up in energy unless I give it energy for it to happen. So that would be a positive energy of the system. Energy went into the system. Another way of showing it is that arrow here. Where did that energy come from? It came from the surroundings. So that one should be negative. So really important part of today is taking away the signs, being clear on the fact that there is a distinct difference between the reaction and everything else, and that they are going to be exchanging energy. The same amount of energy is going to be going in and out. It's just which one is it going into, which one is it going out to? How do we represent that with these energy diagrams? And how does that correspond to the sign of the change in energy for the system or for the surroundings? Okay, so last thing, I already mentioned this, but I want to just formalize it. We talked plenty about how energy can be transferred as heat or work. So that's all this is representing, is that before we just said energy goes in or out of the system and surroundings. Now we're saying it does that either by heat or by work or by a combination of the two. And then recognize that the signs for heat and work are the same as the signs for energy. So since we said negative is most common, let's look at those first. So if energy is going out of the chemical reaction, it's releasing energy, then that means that Q would also be negative if it was releasing energy as heat. Or if it was doing work, if it was pushing on something, the sign of the work should also be negative. So whether you're losing the energy as heat or work, those should both be negative. If you're gaining energy, if energy is coming in, either as heat or work, those should be positive. So real life example of this, you take the Q and you hit the white ball and you provide it 5 joules of energy. Okay, it moves along the pool table, it loses friction, right? Friction is heat, it comes off as heat. It loses some of that energy as heat, 0.5 joules. And then when it hits the purple ball, it does work on the purple ball, right? So it's like the white one is maybe our system. Initially, it has 5 joules. The final is 0. So the change in energy of, I'm just going to put the white ball, final minus initial, so 0 minus 5. So it has lost, that's what negative means, it lost 5 joules. And then the purple ball should just be opposite, or the surroundings rather should be opposite. So some of the surroundings are the table that gains that heat, and some of the surroundings are the work that's done on the purple ball. And those should all be equivalent to however much however much energy the white ball lost, which is why it's 4.5 plus 0.5. So I'll just say the change in energy of the surroundings was equal to the heat and the work, which was positive 0.5 and positive 4.5. Positive because they were absorbing it. Okay, so I know it's a lot of concept stuff, and we're gonna have to like take it and apply it to things. And that's probably more what you're gonna be doing is the applying it part as far as on an exam, but you gotta have this foundation. So like I said, instead of focusing in so much on homework this next day or two, maybe just reread these 2 sections and kind of try to solidify these bigger concepts. We'll do this slide at the beginning of class. It's kind of odd, and I didn't get to it in my other class anyways, so. All right, see you guys on Wednesday. Drive safe if you're driving. Oh my gosh, walk safe. Why did they not clear the sidewalks very well today? Are you serious? The one that's like up here or down? Oh, yeah. Don't park there. Why don't you park in the one up here at the top of Hale? Up here. Oh, but you'd rather do the stairs at the bottom of John Jay?
Yeah.
Oh, okay. Yeah, okay. Yeah, I don't know why they couldn't manage to plow it by 8:30 or 9, whatever. Hi. Good.
Dawson?
Yes. Were you going to come at 10? Weren't you going to come at 10?
I thought it was 12.
Oh, okay. No, that works because I have
sorry.
lots of.
Okay.
No,
My bad.
I
If it was
have
10,
it like
I'm so
written
sorry.
down. No. It's fine. I have like 10 different people that are
Okay.
taking it today, so I probably just got it messed up in my calendar. But like, I had you here, and I was like, "Where is he?" So no, you're good.
Okay, thank you.
Let's just kind of hang out for a
Yeah,
minute.
yeah.
I think I have like 5 or 6 people, so I think we're gonna try to find an empty classroom and just do it in there.
Okay, sounds good.
Yep. Hi.
Can we look at that one example you did? Not this one, the other one, because it was
This one?
no,
Go ahead.
this one.
Okay.
I
Yeah.
was a little confused by that.
Okay. So it says that it's negative. Okay. So negative means it has to go down in energy. It's talking about the system specifically. So for a while, you're going to really have to pay attention to that subscript. So it's telling you for the system, it's negative, which means that our ending one has to be smaller. So it can't be this one because that would be getting bigger.
Okay.
So it has to be one of these two where it's getting smaller. The problem is whatever chunk of energy the system loses, the surroundings has to gain that. So if it started at 3 and went down to 2, that 1 unit of energy has to go into the surroundings. So the surroundings
The
is going to
difference
have to,
goes to
and
surroundings.
yes, yeah.
Okay.
And that's kind of what we meant up here, where we said the system and the surroundings should be the same, just opposite, is like they have to have the same number. They have to have 1 or 2 or whatever. They're just going to be different signs because one's losing it, one's absorbing it.
Okay. And what does this mean? It's
Which
just
one?
a subscript, I think, like this. The R times N. I just didn't know what that was.
Oh, reaction, RXN.
Oh.
Reaction. I don't know why we use an X.
I just wanted to make sure.
No, you're good. So almost always when we talk about the system, we're talking about a chemical reaction.
Okay.
So sometimes I'll write delta E RXN or delta E system.
That
Yeah.
made a lot more sense in like this 2-second conversation than before. I was like, well, how did she get?
Gosh, I know. I don't. This is why tutoring is what it is, you know, because people are like, I would love to just sit down and have someone tell me face to face, one on one.
Yeah. Well,
Good.
thank you so much.
Yep, no problem.
I'll see you Wednesday.
Yep.
Oh, did you ever get to fix that thing?
No, I have it in my list of changes. I'll do grades this afternoon after all these guys take their test, and then it should be in by the end of the day. Yep, you too. Hi.
Do you know what chapter 3 test is? Is it March 20th? But it's spring break, so I was like,
That doesn't make sense. Let me just look really quick because I have like a schedule. Was that on the one I posted on Blackboard just recently, or?
no, it was on the syllabus.
Oh, okay. Then it probably is wrong. So Unit 2 schedule. It looks like March 10th. So this is us up here. So it's like 3 weeks from today.
Okay.
Yep.
Okay. Thank you
Yep.
so much.
Yep. And that's on Blackboard if you need it.
Thank
I don't know why it said